In this video, we're going to talk about function symmetry. Well, what does that mean? Well, a function can be either even or odd. What do we mean by an even function? Well, there's two ways we can check if a function is even. Algebraically, if we replace x with negative x in the formula for a function f, and then we simplify, and we come up with the same formula that we started out with for f, then that's an indication that the function is even. For example, if I look at f of x equals x squared times radical 1 minus x to the power of 4, and I replace x with negative x. Now, negative x in parentheses. We have to remember our rules of algebra when we do this. But after I make that replacement and simplify, I see that I still get the same formula, x squared times radical 1 minus x to the power of 4. So this function f is an even function. Graphically, what does it mean for a function to be an even function? It means that its graph is symmetric with respect to the y-axis. That means that the y-axis divides the graph into two equal parts, which are mirror images of each other. Here are some examples, and we can see why they're called even functions. Because if I have any polynomial that only has even exponents, it will be an even function. Among the trig functions, cosine is an even function. And we may have a function that has a bounded domain, such as a semicircle, which is centered at the origin. One important type of function, which is also an even function, is a constant function. Here I have drawn the graph of f of x equals 2. Its graph is a horizontal line passing through y equals 2. And that horizontal line is symmetric with respect to the y-axis. What about odd functions? Well, again, we have an algebraic test. This time, if I replace x with negative x in the formula for f and simplify, I don't get the same equation or formula back again. I get its algebraic opposite. In other words, I could factor out a negative sign, and what's inside the parentheses would be the original function. Graphically, what does it mean? Well, it means that the graph is symmetric with respect to the origin. It's what we call rotational symmetry. That is, if I were to take the graph of a function and I were to try to make a copy of that function, rotate it through 180 degrees around the origin, then the graph would lie right back on top of it. Let me give you an example here. I need to open a little video. And video, we'll see a demonstration of what I'm talking about. And there you see it. Let me start it again. We have a graph. We rotate a copy of it through 180 degrees. And after rotating through 180 degrees, the copy of the graph lands exactly back on top of itself. So that's what we mean by rotational symmetry. So here we have some examples of odd functions. They would include any polynomial which has only odd exponents. In the trig functions, the sine function is an odd function. And then if we look at radical functions whose indices are odd will be odd functions as well. So by an odd index, I mean we would have a cube root or a fifth root or a seventh root. Those are radical functions with odd indices, and they are odd functions. Now, just by making the observation and the properties of an odd function, we can say that an odd function must pass through the origin. So if I look at the graph of a function and it does not pass through the origin, then it cannot be odd. It might be even. It might be neither odd nor even. But if it does not pass through the origin, it cannot be an odd function. Normally, if we combine an odd function and an even function, we are not going to get a symmetric function. But there are some common combinations or common ways of combining functions which will provide us with an even or odd function. For example, if I add an even function with another even function, the result is an even function. Similarly, if I add an odd function with another odd function, the result is an odd function. If I multiply an even times an even, or an odd times an odd, the result will be an even function. If I multiply an even times an odd, or an odd times an even, the result will be an odd function. And the same thing holds true for division. It reminds us of the rules for multiplying negatives and positives. If you have a negative times a negative, it gives you a positive. So like times like is positive, like times unlike is negative. Here, if we have like times like, it gives us an even function. Like times unlike gives us an odd function. So if we can remember these combinations, it can really help us without having going back to the original definition. So let's look at some examples. Now, what can help us is if we break down as many of these functions as we can as combinations of odd functions and even functions. So f of x, which equals x times sine of x, is the product of an odd function and another odd function. And so the result will be an even function. In our next example, where we have g of x equals x times cosine of x, that's an odd function times an even function. The result will be an odd function. For our next example, tangent of x, well, that's just sine of x over cosine of x, which would be an odd function over an even function. Again, we get an odd function as a result. Cosecant of x is just 1 over sine of x. Now, 1 being a constant represents an even function. Sine of x is an odd function, and so the quotient is going to be odd. In the last example, in the first column, p of x equals x cubed minus 1. X cubed is an odd function, but 1 being a constant represents an even function. And if I add those together, it's going to be neither odd nor even. Moving into the second column, the function q of x equals radical x. It has its domain, it has as a domain all numbers greater than or equal to 0. Now that right away tells us that it can't be a symmetric function, because the definition of either an odd function or an even function has the following requirement. If x belongs to the domain, then the opposite of x must also belong to the domain. And so since the domain of q of x does not include any negative numbers, then it cannot be a symmetric function. So it is neither odd nor even. The next function is phi of x equals radical x squared plus 1. In this case, the domain is all real numbers. We have to go back and use the definition of odd and even, and by using the definition, we will find that this function is even. Our next equation, or our next function, is a rational function. R of x equals x squared plus x all over x cubed minus 1. In this case, neither the numerator nor the denominator is a symmetric function. We still should be careful and go back and use the definition, but in this case, in almost every case, it's going to result in neither an even nor odd function. And in our last example here, u of x equals x squared minus 1 all over x cubed plus 2x. We have a rational function. The numerator is an even function. The denominator is an odd function. So the quotient is going to give me an odd function. Well, I hope you've enjoyed this short video on even and odd functions. It is a very useful topic to understand, and we'll be using it throughout the rest of the course.